So when we're doing this kind of things, you need to be able to take your brain away from concrete numerical things and start getting into some strange abstract things. Right? This is a big leap for a lot of students to do because they're used to numerical answers, right? A picture with a certain length. Well, now we're not going to have those. It's going to be completely abstract, which is very, very hard, I understand, but just bear with me. Hopefully it will make more sense in 20 minutes when we're done. So we're going to ask to prove that the opposite sides of a parallelogram are parallel. Okay? So think about Algebra 1. When lines were parallel, what were true about those lines is equations. They had the same slope. So we're going to design, right, a parallelogram, and we're going to find the slopes of the opposite sides. Okay, remember, slope is y minus y over x minus x. That's the formula that we're going to use in order to calculate a slope. Okay, so we're going to put one corner in the lower left-hand box of our coordinate grid. So right here, we're going to call this point 0, 0. Right, that's our coordinate here at 0, 0. That's the origin of your graph. Okay, so a parallelogram, we're going to come over and we're going to talk about this first point right here. Okay, so maybe this is point A, this is going to be point B. So we have to decide what are the coordinates that go along with point B. Okay, so you've gone a certain distance in the x direction and you've gone a certain distance in the y direction. So you have to decide what letters are you going to use to represent those two lengths, right? Because you can't say it's 4, because now it's a specific parallelogram. And you would have to prove for every single parallelogram with every single number ever, which is 1,000,000 proofs. You don't want to do 1,000,000. You better like doing 1. So we're going to say that we have gone, I don't know, x units in the horizontal direction. And we've gone, let's see, how about y units in the vertical direction? Okay, remember this is the side or the leg of your parallelogram right there, side AB. So what are the coordinates that go along with B? X, comma, y. We've gone x units horizontally and we've gone y units vertically. Perfect. So there's your first little foray into making a random generality statement. Right? Because now we're talking about any x and y that you could ever pick. Okay, so next we need to move over some more, right, to get to our lower right endpoint. So here's the point, we'll call this one D, because right, you have to go around in counterclockwise order. So A, B, C will be over here somewhere. So this is our last point, D. So the question is, how far, how much further do you want to go past your x distance? You want to do z? Okay, so we'll call this length z. So from here to here is denoted as z units. All right, so we can't use x. We've already said that x is this much. This is your x distance. So you can't do that again. So we have to use a different variable. So if that's z, what are the coordinates of point D? X plus z, right? We started at 0, 0. We start at the origin. You start at the origin, and we come in the direction of D. So we've gone that far. So you've gone x units, and then you go another z units. And our y coordinate is 0, right? Because you have gone 0 units up and down off of the x-axis. Now, to have a parallelogram, I need to make sure that my top is the same slope and it's the same length. Okay, so what was the length of my bottom side? X plus z is the length of my bottom side, and the property of a quadrilateral or a parallelogram is the top has to be the same length as the bottom. So if I have another x plus z length on top, what are the coordinates at point C?
X plus z on 1.
Okay, so let's start at the origin, right? Start at the y-axis. Start at the y-axis right here. How far have I gone to get to point B? How far have I gone from the y-axis? I've gone x units to get to point B. And then from point B, how far do I go to get to C? It's x plus z, right? This from B to C is x plus z units long. But I also have to go x units off of my axis here. So from my axis all the way over to point C, how far have I gone? 2x plus 1 z's. Okay, we're starting at the axis because that's where we start counting from, your axis. So I've gone 2x plus z in the x direction, and how high in the y direction? Y. Okay, and then of course you connect your parallelogram by drawing your line back to there. Okay, so we have done a perfect job. We are x units away, right? This is x units. Our first dot point B is x units from your axis, and then you go another x plus z, because that's the length of the bottom, right? These have to be the same in a parallelogram. So you go 2x plus z to get to point C, and you have gone y units up. Okay, so that's the hard part, right? You've never been asked to do this before, to the best of my knowledge, in any math class up to this point. Okay, but this is true, right? These are real, right? If you put numbers to them, then you actually have numerical coordinates that will be a real parallelogram. So we're asked to show that the opposite sides are parallel by using slope. Okay, so let's first tackle our top and our bottom. Okay, the top side and the bottom side. So we're going to find the slope of BC, and we're going to find the slope of AD. Okay, those are opposite sides. So let's remember, slope is found by doing y minus y over x minus x. So m is your variables for slope, and we're finding the slope of line BC. Okay, now what can you guess that's going to be? It's probably going to be 0, right? Because we have our bottom side is directly on your x-axis. So let's see. If we're going to use our slope, that's y minus y. Okay, so y1 minus y2. So the y-coordinate at point C minus the y-coordinate at point B. Over the x-coordinate at point C minus the x-coordinate at point Z. So 2x plus z, that's the y-coordinate at C, minus x, that's the x-coordinate at point B. Okay, so when we do this simplifying, what do we get in the numerator? Y minus y is 0, and 2x plus z minus x is x plus z. Now, according to life, 0 divided by anything is 0. So that slope from B to C is 0. No. Undefined is where we have a vertical line and you have 0 in the denominator. If 0 is in the denominator, you have an undefined slope. If 0 is in the numerator, then you have 0. So now let's find the slope of the opposite side, which is AD. And we're going to do a similar thing. We're going to take the y-coordinate at point D and subtract the y-coordinate at point A. And as you can see here, that's 0 minus 0. So even though, right, this is an exercise in futility, because 0 over anything is going to be 0. Okay, which is exactly what we wanted, because what's the slope of the top one? 0, and the bottom one is 0. So if you have the same slopes, then your lines are parallel. So that shows that the top line is parallel to the bottom line. So now let's tackle the non-horizontal lines. So side AB and side CD. So once again, we're trying to find slopes. Okay, remember we're finding slopes. So y minus y over x minus x. So what is the y-coordinate at point B? Y minus
0.
0 over x minus 0 is just y over x. Okay, so that's the slope of line AB, y over x. Now let's do a similar thing for DC or CD. Okay, so the y coordinate of point C is y minus the point there is y minus 0. And then our x's, we have 2x plus z minus parentheses x plus z. Okay, y minus y over x minus x. So let's do this subtraction. 2x minus x is 1x, and then z minus z is 0, right? So we have a slope of y over x. And by Jove, that's exactly what we had on the other side. So those are parallel also. So we have shown with coordinates, right, with using letters for coordinates, that the slope equation for these sides are the same, and the slope equation for your non-horizontal lines are also the same. Okay, so no matter what x and y you pick, you're always going to have the same slope. Okay, so pick any one of the billions of numbers for x and y, the coordinates, and you're always going to have a parallelogram, as long as it starts at, of course, 0, 0. Okay, so that's kind of how our thought process is going as we prove these things about quadrilaterals. So the next thing we have is a rhombus. Okay, so with a rhombus, we are not going to start at the origin, okay, because of course, hopefully you know a rhombus is a 4 equal-sided parallelogram. So that's kind of what we're going to draw on our paper. Okay, so let's start right here. This is going to be our left point A. This is going to be this point, representing this. Okay, so what are the coordinates of A? Y comma 0, something comma 0, right? You don't have to use x and y. Just for fun, let's make up another letter. Let's use M. Okay, so this is going to be m units up, so our coordinate is 0 comma m. Okay, and then let's go over to here. So how far do you want to go over? Any letter you want to, but let's just pick n for fun today. So this is n, right? This represents point B down here. So what are the coordinates for point B? N comma 0. Okay, so now, right, let's go to point D. Sorry, that's not point D. We're going to call it point C because you want to go in order as you go around. So point C will be here, right? So where would point C, how far to the right have we gone to get to point C? In order for this to be a rhombus, it would be another n. Okay, so how far have we gone to the right for point C? 2n, or n plus n, right? To get to there, it's 2n, and then our y value is m, right? Because we need this to be a bisector. One of the properties of all parallelograms is that the diagonals bisect each other. So the length from A to the middle needs to be the length as from the middle to part C. In order for it to be a rhombus, that has to be bisected. So that's got to be the middle, which is why that's 2n. Okay, similarly for the other one, the last point, this distance has to be the same as that distance. So what are the coordinates of point D? 1n and 2m's. 1n and 2m's. Okay, so that point should be right, twice as high as your middle. I'm just going to erase some of this here. It looks pretty sloppy, sorry. Right, because this is your diagonal. The diagonals need to meet in the middle of both of them. That's one of the properties of a parallelogram, is that the diagonals get bisected. So now when we draw your rhombus, right, we connect the dots, your A, B, C, D. We want to show that these lines are perpendicular. Okay, the diagonals are perpendicular. The point in the middle is not a named, I guess we call it point E, I guess, in our classroom, we call it E, right? But for us in our proof, we don't need to have that point labeled. Okay? So perpendicular, if our lines are perpendicular, what's true about their slopes? Negative reciprocals. Okay? If you have perpendicular lines, they have a negative reciprocal slope, like 2/3 and -3/2. Okay, maybe you remember that from your Algebra 1 class. Negative reciprocal slopes are perpendicular. Okay, so we're going to find some slopes once again. So let's start with our diagonal DB. So what is the slope from D to B? Well, y minus y over x minus x, right? So we have 2m as the y coordinate minus 0 as the y coordinate. And we have n as the x coordinate at D, and we have n as the x coordinate at B. So our slope is 2m over 0, right? Which is, of course, an undefined slope. But 2m over 0 is a slope from D to B. Okay, perfectly fine slope, right? Don't get upset because it's not a number. That is a perfectly happy little slope. And now let's do the same thing for our other diagonal, AC. So the slope from A to C is once again y minus y, which is m minus m, divided by n to n minus 0, which is 0 over 2n, which comes out to be 0. Okay, so hopefully you remember from your Algebra 1 class that these are in fact negative reciprocals, right? They're definitely, we had a 0 on the bottom for your blue line, and we had a 0 on top. So those things got reciprocated. Now I don't know what 2m or 2n is, but undefined slope and a 0 slope are perpendicular, right? That's a vertical line and an exactly horizontal line. So yes, in fact, we have a perpendicular slope. Okay, so we're finding slopes if you want to know if something is parallel or perpendicular. So our last example, prove that the diagonals of an isosceles trapezoid are congruent. So we need to graph an isosceles trapezoid. Okay, so isosceles trapezoids have parallel bases and congruent legs. So let's start by putting our first coordinate here at 0, 0. So our first point here, B, or rather our second point, we have to decide how much to the right and how much vertically do we want to go, right? And you need to put a letter there for each of them. So whatever your favorite letter is today, use that one.
Let's do H.
H is a nice letter, and how about J? H and J. So point B has the coordinates H, comma, J. So my commas and my J's look a lot alike, unfortunately. I'll make that smaller, so make my J bigger. There we go, H, comma, J. So there's our first line. Now think about an isosceles trapezoid. We have to go parallel. How far do you want to go parallel to get to point C, right? That's our next question, is how far is it from B to C? And just to stay with this letter grouping, let's use K. So what are the coordinates of point C? H plus K, comma, J. Because once again, we're starting at the axis, we have to go h units to get to point B, and then we go k units to get to point C. So h plus k, comma, j. So if we think about this isosceles trapezoid, an isosceles trapezoid is a rectangle that has two congruent right triangles glued onto the edge. Okay, so if I want to get to my last point, point D, I need to go another how many units? I need to go another h units in order for this to be equal, right, on the right and the left. In order for those lines to actually be the same length, I have to go the same distances. So the same distance means I have a letter already assigned there. So point D is at 2h plus k, comma, 0. Okay, so you've done the hard part, and that is labeling your coordinates correctly. Okay, there's lots of ways to label it incorrectly, right, using all kinds of different letters. But in order for it to be an isosceles trapezoid, you have to do it kind of special-like. So we want to show the diagonal. So let's draw in a diagonal. Here's a diagonal from C to the A. From C to A, there's a diagonal. Okay, so what we're going to do is we're going to drop in our vertical line here and make a right triangle so that I can figure out this length by using the Pythagorean theorem. Okay, if you can make right triangles, then you can use all kinds of nice algebra or kind of geometry here. So if I'm going to use the Pythagorean theorem, what's the length of the bottom of my right triangle? H plus k. So h plus k quantity squared plus what's the height of my right triangle? J is the height, so j squared equals d sub 1, the first diagonal, squared. So if I wanted to solve this equation for d sub 1, how do I get rid of this square? I take the square root. If you're squaring something, to undo a square, you take its square root. So d1 is the square root of h plus k squared plus j squared. And that's your equation, right? That's done. That is what the Pythagorean theorem says. That's as nice as you need to have it. So there's one diagonal length. So let's come back and make another diagonal. So here's BD diagonal. And we're going to drop another vertical line and make another horizontal line so we have a right triangle. Okay, so this is D2, the second diagonal. D2 squared equals, what's my long leg on the bottom here? K plus h squared plus my vertical side is j. So then I solve by taking the square root of both sides, and I get d sub 2 is the square root of k plus h quantity squared plus j squared. So are our equations the same? That's the question. And even though we have h plus k and k plus h, right, according to the property of the commutative property, h plus k is the same as k plus 8, right? 1 plus 5 is the same as 5 plus 1. So this order doesn't really matter because you're adding the same things together. So sure enough, these two equations are the exact same, which means the distances of those, or the lengths of those diagonals, are the exact same. Okay, so this is how we do coordinate proofs, right? You pick some letters, you apply them correctly to the vertices, and then you use slope if you want to find something being parallel or perpendicular, and you use the Pythagorean theorem if you're trying to show something is congruent by finding their lengths. Fantastic.